In today's video, we'll learn about the Doppler effect. Majority of us have most likely experienced the Doppler effect at least once in our lifetime. For example, when a cop car siren is blowing, the frequency of the sound you hear is higher as a vehicle approaches you and lower as it moves away from you. This is a classic example of the Doppler effect. Although as a vehicle approaches we hear a higher frequency, and as the vehicle moves away from us, we hear a lower frequency. It's important to remember that the frequency of the source remains constant. And so we see that the Doppler effect can be applied to all common waves, even including light waves. The equation we use to explain the Doppler effect is F naught, which is the frequency of the Doppler, is equal to the frequency of the source, which is our F subscript S multiplied by V, which is the speed of sound, plus or minus V naught, which is the speed of the observer, divided by V plus or minus Vs, which is the speed of the source. In order to fully understand the Doppler effect, it's necessary to know when to use a plus or a minus sign within the equation. So to summarize, we know that as the source of the sound approaches, the frequency we hear is higher. So if we look at our equation, if the frequency is going to be higher, that means our numerator is going to be a larger number. Therefore, when the observer is moving towards the source, we'll have V plus V naught. And if the source is moving towards the observer, in order to get a higher frequency, we'll have V minus Vs. Now, as if the frequency we hear is moving away from us, we can look at our equation, and we see that if the observer is moving away from the source, our frequency is going to be lower. Therefore, our numerator is going to be smaller. So on top would have V minus V naught. And if the source is moving away from the observer, we know we would hear a lower frequency as well. Therefore, we would get V plus Vs. And this can be summarized in our figure to the bottom left, where we're given 4 different examples of 4 different scenarios. So let's see which scenario applies to our example below. In our example, it states that an airplane is traveling at half the speed of sound, which emits a sound frequency of 5 kHz. And we're asked, at what frequency does a stationary listener hear the sound as the plane approaches and after it passes? So we know V stands for the speed of sound, which according to our example, the speed of sound is equal to 344 meters per second. And it says that the listener is stationary. Therefore, the velocity of the observer is equal to 0 meters per second. And the velocity of the source is equal to half the velocity of sound, or equal to 172 meters per second. And we're given that the frequency of the source has a frequency of 5 kilohertz. So in part A, we're asked what frequency does the listener observe as the plane approaches. So using our Doppler equation, we have the frequency of the Doppler is equal to the frequency of our source multiplied by our velocity plus or minus the velocity of our observer divided by the velocity of sound minus or plus the velocity of the source. Well, since our observer is stationary, we know that our equation can be written as just the velocity of our speed in the numerator. And now we need to determine if we'll use a plus or minus in the denominator. And since the airplane is approaching, we should observe a higher frequency. And so in order to observe a higher frequency, our numerator must be minus the velocity source. So if we plug in the information we're given that the frequency of the force is 5 kilohertz multiplied by the velocity of sound divided by the velocity of sound minus the velocity of our source, which is half the velocity of sound. So if we were to simplify our equation that's in the brackets, we would get 5 kilohertz multiplied by 2. Therefore, the frequency of the Doppler that the listener would observe would be 10 kilohertz. In part B, we're asked, what frequency does the listener observe as the airplane moves away from the listener? So, still using the Doppler effect equation, our observer is still stationary, therefore our numerator will still just be the velocity of sound, and our denominator will have the velocity of sound plus or minus the velocity of our source. And since we know that as the source moves away from the observer, we observe a lower frequency. And in order to get a lower frequency, our value within our brackets must be smaller. Therefore, in order to get a smaller value, our denominator must be a plus. So we can rewrite our equation where the frequency of the source is still 5 kilohertz multiplied by the velocity of sound divided by the velocity of sound plus the velocity of our source, which is 1/2 the velocity of sound. And so if we were to simplify our equation, we would get that 5 kilohertz multiplied by 2/3. And when we do so, we see that the frequency that we would observe is equal to 3.33 kilohertz, which this makes sense, since in part A, the airplane is moving towards the observer, so we should hear a higher frequency, which we heard was 10 kilohertz. And as the airplane moves away from our observer, we should hear a lower frequency, which is 3.33 kilohertz, which is smaller than the frequency we heard in part A. In our second example, it states that two trains on separate tracks move towards each other. Train 1 has a speed of 36.1 meters per second, while Train 2 has a speed of 25 meters per second. Train 2 blows its horn, emitting a frequency of 500 hertz, and we're asked what is the frequency heard by the engineer on Train 1. So Train 1 has a velocity of 36.1 meters per second, and since the engineer is on Train 1, this will be the velocity of the observer, which is 36.1 meters per second, and Train 2 emits the frequency of 500 hertz, traveling at a velocity of 25 meters per second. So the velocity of the source is traveling at a velocity of 25 meters per second. And the frequency of the source emitted by Train 2 is equal to 500 hertz. And the engineer on Train 1 is the Doppler frequency that the engineer will hear, which is unknown. So if we use our Doppler effect equation, we see that F naught is equal to Fs multiplied by the speed of sound plus or minus the velocity of the observer divided by the speed of sound minus or plus the velocity of the source. So we know all our variables besides the frequency that is heard, which is what we're trying to solve for. So we can plug in the frequency of the source, which is 500 hertz, multiplied by the speed of sound, which is 343 meters per second, plus or minus the velocity of our observer. So since our observer is approaching the source of our sound, he's going to hear a higher frequency. In order to hear a higher frequency, our numerator must have a higher value. So in order to get a higher value, we would have a plus sign in our numerator. So plus 36.1 meters per second divided by the speed of sound plus or minus the velocity of our source, which was 25 meters per second. And since our source is moving towards the observer, we'll hear a higher frequency. In order to get a larger value, our denominator must have a negative sign. So if we are to calculate this out, we see that the frequency that the engineer hears on train 1 will actually be a frequency of 596 hertz, which should make sense since our observer is heading towards the sound and the sound is approaching him. He should hear a higher frequency, which we see is true since our emitted frequency was 500 and our observed frequency was 596 hertz.